Our final lesson in this section is some cautionary notes about when we combine multiple individual estimates. First of all, some positive news. That is, we can decompose things. Maybe initially we can't decompose them much, only systems or groups. But as we get further along in the life of the project, further along in the cone, then you start knowing, not speculating, individual work items. Since they are smaller things, there are more of them. As we increase the number of items in a bottom-up estimate, our accuracy improves. That is, we have a math thing that says that the sum of the errors tends to be less than the error of the sums. That is, given a large enough pool of items, that overestimation errors and underestimation errors will start to cancel each other out. Or simply, the average of the pool becomes a good number for estimating and overall planning. The accuracy of the average is reasonable enough for you to say, I don't know what any individual item in this pool is, but on the average, they're X. Have a large enough pool of similar work items, the average times the number of the items in the pool will predict reasonably well the size of the overall pool. Any given individual item in the pool is probably not equal to the average. Some are over and some are under. In fact, if it's a good average, about half will be bigger and half will be smaller. Yeah. Maybe none will be exactly the average. Still, the average will be a good predictor for the pool overall. So that's the good news about combining individual estimates. We can use the average and have to know every item in the pool. Also, the middle number is hopefully close to a true 50-50 because that is where our cautionary note comes in. We're dealing with probabilities here, and thar be monsters. Adding probabilities is not for the faint of heart. To illustrate adding probabilities, let's just imagine here I have an equally balanced spinning wheel where I have the numbers 1 through 10 on it. I will give it 10 spins and add up the numbers. Let me give it a spin here. It comes up with a 5. I do this 9 more times and I add up the number from each spin together. If I try the experiment, what's the possibility of me getting a number less than 10? Well, 0, because 1 is my smallest number, and I could spin and do a spin that lands on 1 10 times in a row. The sum will equal to 10. What are my odds of actually spinning a 1 10 times in a row? There are 10 billion possible combinations, and so getting a sum of 10 exactly is 1 in 10 billion. To figure out all the other numbers, I had a mathematician figure those out for me. There are a couple of interesting insights. We walked around and asked for everyone's best case, a number with 25 or 30% confidence. What would that turn out look like? Well, look at the number 20 here. If we walked around and asked for everyone's best case and try to add those up, we get a number that has a vanishing small probability, 0.0018%. This is not going to happen. On the other end, I had one director ask for everyone's worst case number, a number that we had 90% confidence in. You try to add those up, you don't see it 90%. You get something numbers like 99.9999999%. We start seeing is that if we get numbers below 50 or numbers above 50, we quickly start heading toward the extremes. Almost impossible or certainly guaranteed. What percentage can we add together and keep the same percentage? There's only one, and that's the 50-50. On the example spinner, 54 is our true 50-50 number, and in the calculation, 55 or less keeps us right around 50% when we add up all the spins together. When we add estimates together, we need each to be the 50-50, the nominal estimate. Anything else quickly skews the probabilities. Here are some strategies to get a 50-50 to combine with other estimates. The first is that we have a good estimator, perhaps someone who's mastered this class. They have done the estimation work well and have given us a 50-50. Beautiful. Our experience and the data suggest those people are pretty rare. What we tend to get from an individual is a best case. We can take that best case and, if we had a calibrated multiplier, use that to get a range. The midpoint may work here. However, in general, selecting the midpoint has some issues. Remember that our probability is not symmetrical. The distance from the best case to the nominal is often way shorter than the distance from the nominal to the worst case. So a midpoint there might be too big. If the worst case was also an estimate, not a calculation, then it's likely to have some human optimistic bias and not be the worst. A midpoint probably wouldn't work there either. A better solution for when we have a whole range is where the worst case is estimated, not calculated, is to use a 2/3 point between the estimated best case and the estimated, not calculated worst case to deal with the bias. It will probably be a bit over, but remember, if you recall, it's slightly better to overestimate than to underestimate effort. Of course, even better would be get the 3-point estimate, as we've talked about, and run the PERT formula. This will give us our best chance at a 50-50. We've got a calculated worst case, but we still come back to reality with our most likely case. And you don't need to use one technique. You can combine and come up with your own. Our goal is always to get an individual estimate to the 50-50 as best we can. 3 notes you might want to walk away with from this lesson. First is the accuracy of the average is actually reasonably good. It's not perfect. I wouldn't necessarily bet my next paychecks on it, but it's helpful to make good business decisions. We can use the accuracy of the average. Probability is weird. If we're adding individual estimates together, only the 50-50 estimates will maintain the same 50-50 probability. Estimates with higher or lower probability will quickly skew the overall probability. Finally, how do you get to that 50-50 estimate for each individual estimator? Your best bet is still using our friend the PERT formula. That's the safest one, and that's the one I recommend. If you can't get a most likely out of the estimator, but you still can get a guessed best case and worst case, then the 2/3 can work. But I would like to go back and use the PERT if possible.